Good morning, everyone, or I guess good afternoon or good evening, depending on when you're watching this. Today we will finish up our last section from Algebra Chapter 11 with 11.3, which is going to have two targets. First one being that we can solve equations that contain radicals, and specifically square roots. We're only dealing with those. And then also, can we identify these things called extraneous solutions? We've come across that a couple of times this year in different types of equations, so we'll again kind of refresh our memory on what those are and how you can identify whether or not one of your solutions is in fact extraneous. So first of all, we began this chapter by simplifying radical expressions. We then did some operations with radicals, and now we're looking at solving radical equations. So a radical expression was any expression that contained a radical. Similar to that, a radical equation is any equation containing a radical. And then when it comes to an extraneous solution, that is a solution that you arrived at mathematically. You took all the right steps in the process of solving the equation, but then when you went back and actually checked your answer in the original equation, it doesn't actually satisfy the original equation. So it is a solution arrived at mathematically, yet it does not satisfy, sorry for my sloppy handwriting, the original equation. So we took all the right steps mathematically, but the answer we got actually is not an answer. So what that means for us is, and this happened back when we studied absolute value equations, is that we just want to be extra careful about checking all of our answers when we're done solving these equations. So with these first four examples, I'm going to do these three with you. I'm going to save this one for you guys to kind of try on your own if you'd like. It says solving by isolating the radical. So that's always going to be your goal, if possible. If there is a single radical, as you can see, all four of these just have a single radical in the equation, your first goal is to isolate it. So up here, if I kind of like box out the radical part of this, I can see that this minus 5 is not underneath of that radical, or in other words, it's not part of the radicand. So for me to isolate what I just boxed out, I'm going to have to move that minus 5 over here. So I'm going to go ahead and say plus 5 to each side. Those are going to cancel out. I'm just going to carry this over here because there's not room. So that would leave me with the square root of x, and then I know over here 4 plus the 5 would give me a 9. Now I can see that the square root of x is alone or isolated. So to get rid of that, we have to use an opposite or an inverse operation. So square rooting is the opposite of squaring. So if we square the square root of x, we will just get x. And if we square the left-hand side of this equation, we've got to come over here and do the same thing. 9 squared is 81. So this is like halfway done. We get an answer, we think, of 81. Now what we have to do is take that and go back to the very original equation, which is the square root of x minus 5 equals 4, and plug that in to make sure that it actually is an answer. So I'm going to just do some mental math here. If you'd like to write it down on your paper, you can. So imagine the 81 replacing the x. I know that the principal, because it's the only square root you take when you check is principal or positive. The principal square root of 81 is 9, so that would then turn into a 9, and then 9 minus 5 does equal a 4. So this answer is good to go. It is not extraneous. Now let's try another one down here. We have the square root of x plus 7 equal to 12. So as you can see, they're pretty comparable, just different numbers here. So once again, if you want to box this out, highlight it, do whatever it is to kind of like pinpoint where that radical part of the equation is, that plus 7's got to go because it is not included in the radicand of that radical. So those cancel. Now we do have some room underneath here. 12 minus 7 gets us a 5. And then again, to get rid of the square root, you're going to square. So x would equal 5 squared, or 5 times 5 gets us a 25. And maybe for this one, I'll show the work on the paper for checking the answer. So I'm going to go back up to the original. I'm just going to rewrite the original equation with 25 substituted in for x with a set of parentheses. So I'm going to say the square root of 25, and then plus 7 should equal 12. If it doesn't, that means that this is an extraneous answer. All right, now the principal square root of 25 is 5, so next I'd bring down 5 plus 7 should again equal 12, and in fact it does, so 12 equals 12 means our answer is good to go. So again, not extraneous. We'll skip over B. If you look at C, it also just has a single radical. The only difference now is that there's not just a variable in the radicand. Now you have a variable expression. So you've got the C minus 2. All of that is under the radical. So if you were to think of boxing that out, the radical is alone because everything's underneath of it. So the next step would then be to get rid of it. So what you would do is you'd say square and square. So squaring undoes square rooting. So anytime you square the square root of anything, you are left with the radicand. And in this problem, the radicand is the expression C minus 2. And then over here on the right, 6 times 6, or 6 squared, is 36. And now we have a little bit of extra work to do. We would have to add 2 to both sides. Those are going to cancel. 36 and 2 make 38. And then this one again, let's go mental math. If I imagine coming back up here and plugging in the 38 for C, first I would have to do 38 minus 2 in the radicand, and that would give me 36. And then I'd take the principal square root of 36 and say that 6 does equal 6. So this solution is also good to go. So far nothing has come out to be extraneous. I think we'll come across that on the back side. All right, next type of situation would be where maybe you don't have just a single radical in the equation, maybe you have 2. And if you look at this problem, everything on the left side as well as on the right is underneath of the radical or part of the radicand. So here, the first step will have to be for you to square each side so that you can get to what's underneath of those radicals, those square roots. Think of the square roots as like protecting what's under them. You can't do anything with that part of the radicand or any part of the radicand until you get rid of the square root. So that's why the first step here would be to square both sides. So again, when you do that, squaring undoes square rooting. You're left with just the radicands, and now you just have a simple linear equation. So you've got 4 options. I'm going to go ahead and do 2 things at once here. I'm going to bring the 2x to that side by subtracting, technically from both sides. I'm also going to bring that minus 4 over there by adding 4 to both sides. So kind of working left to right, 3x minus 2x would give me 1x, or just x. When I add the 4 to that, negative 4, those are going to cancel. So that's all I have now on my left side. On the right side, when I take 2x away from that 2x, those will cancel. And then the 3 plus the 4 that I brought over would give me 7. So we get an answer of 7. I want to know if that's right. So I'll come back to the original. If I take 7, I will show the work on this, and I plug it into the original. You would see whether or not 3 times 7 minus 4, the square root of all of that, is equal to the square root of 2 times 7 plus 3. 3 times 7 is 21. Still have your minus 4. 2 times 7 is 14, plus your 3. 21 minus 4 gets me square root 17. I'm just going to leave that there. And 14 plus 3 also gets me square root 17. So square root 17 does equal itself. So that is the solution to that equation. Similar situation here. 2 square roots or 2 radicals, everything is underneath of them. So to touch anything in that radicand, you got to get rid of the radical. So we got to jump right in by squaring both sides for the first step, leaving us with the radicand of each of those sides of the equation. And then back to, again, a linear equation. Let's go ahead and bring 5t over there by taking 5t away from each side. Let's bring the 4 over here by subtracting 4 from each side. 3t minus 5t, I'll carry this here, would get us a negative 2t. And then that 4 minus that 4, those will cancel. So that's all we have on the left. Over here, that 5t minus that 5t will cancel. And the negative 6 that's already there minus 4 more would be a negative 10. And then because negative 2 is being multiplied by t, the opposite of that would be to divide, to get rid of that negative 2 so that we can get t alone. Cancels. T would now equal a negative divided by a negative is a positive. 10 divided by 2 would give us 5. And then from there, if we come over here to check, the square root of, it used to be 3 times t, so I'm going to throw the 5 in there for that t, plus 4, should equal the square root of 5, used to be times t, throw the 5 in there as well, minus 6. 3 times 5 is 15, I'm just going to throw that under here, and 15 plus 4 is 9, so root 19, hopefully we get another root 19 over here. 5 times 5 is 25. 25 minus 6 is also 19. So root 19 does equal root 19. That would be our answer. All right. So now let's finish up with this last situation where they're saying identifying extraneous solution. So I'm willing to bet that might happen in this problem. And something else you're going to have to kind of remember is back in chapter 10, we spent about a month and a half studying quadratic equations. This type of situation will require you to end up solving a quadratic equation. So kind of think back to your options. Square roots is the easiest, but not always an option. Factoring would be the next easiest. And then if neither of those are options, you're probably going to want to use the quadratic formula. So as you can see, we're back to the situation where we just have one radical, but on the other side, now there's a variable. Whereas if you flip back to that last page when we were in this situation, there was another number over there. So when we go to get rid of, because this is, if I box this out, it's alone. So to go any further, I have to get rid of it. When we go to square both sides, what ends up happening on this side is we get an x squared, which then makes you think, oh, this is now a quadratic equation and no longer just a linear equation. So you bring down the x squared, you bring down the radicand of that radical portion of the equation, and then I'm thinking we might want to get this in standard form. So I'm going to swing the x and the 12 to the left, because I usually want to keep a positive leading coefficient on any quadratic equation. So if I subtract x and I subtract 12 from both sides of the equation, so I'll show that, minus x, minus 12, cancel, cancel. So on the right, you have just a 0. And then over here, putting these in standard form, the exponent should decrease from left to right. So you're going to want this out in front, followed by that, followed by your constant. So looking at this quadratic equation, it's gone from a radical equation to a quadratic equation. We know sometimes quadratic equations can have 2 solutions. It could have 2, it could have 1, or none. Think of like parabola intersecting the x-axis. So I know that using square roots is not an option here because we have a b value of -1, or we have this linear term that would kind of get in the way of us isolating x squared equal to a constant. So next I'm going to see if this is factorable. I'm noticing that it is a trinomial with a 1 in front, so you'd have to use your factor sum method. So are there factors of -12 that also add up to -1? And I'm thinking -4, +3. So because -4 times +3 is -12, there's your factors of that. And -4 plus 3 sum to -1, so factors of that sum to that coefficient on x. We could factor this down to x. I'm going to grab that -4 first, so x minus 4. And then the 3 would give us a binomial factor of x plus 3 equal to 0. And then you apply the zero product property at this point, which is where you take each of those binomial factors and imagine setting them equal to 0 and solving. I will actually do that. So if I take x minus 4 and I set that equal to 0 and solve for x, I'd have to add 4 to each side. I get one solution, potentially, we're going to have to check it, of x equals 4. And if I take the other linear factor of x plus 3, set that equal to 0, I would minus 3 from each side. The other answer I get is -3. So here we got 2 possible answers. So if we come back up to the original equation, let's just do some, again, mental math here. Let's not do mental math. Let's actually plug it in. Let's do the 4 first. So we have to plug it in 2 places, there and there. So I'm going to start by saying, does 4 equal the square root of 4 plus 12? I know 4 plus 12 is 16. And if I take the principal square root of 16, I get 4. So 4 does equal 4, which means that is an answer. 4 is a solution. If I do the same thing with the -3, does -3 equal the square root of -3 plus 12? -3 plus 12 is 9. But again, when you're checking these, you only take the principal root of that number. So the principal, or the positive root of 9, is 3. 3 does not equal negative 3. Therefore, this right here would be an extraneous solution. So just put ext next to it. So I always, back in the classroom anyway, we would always tell you guys that if this were a quiz question and this were the answer line, the only thing you'd put on that answer line is the x equals 4, because that's the only actual answer. This is an extraneous. We would just expect to see this in your work somewhere. So just a kind of quick follow-up to that final question. It says in that last example, how could you have determined that the negative 3 was not a solution to this equation without having to go through all of this work that we just did, even though it wasn't a ton of work, without having to go through that work? So here's what I would kind of think of. If this right here is a negative number, and we're only taking principal or positive square roots of these radicands, we know that when we do that, we're going to get positives. A negative number will never equal a positive number. So that's a way that you kind of, as you move forward and see more situations like this, you would know that is not going to check out. But if you feel like you might not catch that, then maybe just plug it in every time or do some quick mental math, check it that way. But either way, you do want to make sure that you're checking, because this is something that can happen often with this type of equation. Alrighty. Have a great day, great afternoon, great evening, and I will see you guys again when we begin chapter 12.